This video will focus on naming ionic compounds. So we'll work on writing the names and the formulas for binary ionic compounds and also ionic compounds that contain the stock notation where they need Roman numerals. Whenever I say the binary ionic compounds, it just means two elements. So every time you see a name or a formula in this particular video, you'll notice it's just between two elements. When we have more than two elements, so a non-binary situation, we will deal with that in the next video. So just to review, when we talk about ionic compounds are those compounds that are formed when an electron is transferred. So upon transfer an electron, one atom becomes positive, one becomes negative. They're not electrostatically bonded to one another because of the opposite attractions. One pattern you're going to notice when you look at all the formulas or names is that ionic compounds must have a metal bonded to a nonmetal, or more generally, a cation with an anion, because the whole point of an ionic compound is that you have two charged particles that are bonded together, causing them to be neutral. So the huge thing to notice when we go through naming and forming formulas for ionic compounds is that when two different elements come together to make a compound that is ionic, the ions they make have to create a ratio so that their charges add up to be zero. Okay? So the amount of positive cations you have in terms of charge has to be canceled out with the amount of negative ions we have. The way we make that happen is sometimes we use multiple ions of any one given element. So essentially what this is saying to you is that when ionic compounds come together, yes, they're binary because they're two different elements, but they don't always come together at a ratio of 1 to 1. It's not always one atom of the cation and one atom of the anion. Sometimes it's a ratio of 1 to 2, 2 to 1, 3 to 2, okay? That ratio is really the heart of the confusion usually for ionic compounds, because you have to figure out what ratio it is depending on the name or the formula to get the formula or the name right. There's only one correct ratio. If you have a positive 1 ion and a negative 2 ion, there are not multiple ways those two ions can come together to make a neutral atom. Because there's only one combination that creates a neutral atom, we don't use prefixes like we did with the molecular compounds. We don't need prefixes because when I say the term magnesium chloride, there's only one way magnesium and chlorine can come together in an ionic compound to add up to a charge of 0. Okay. So again, the heart of this is not learning prefix for ionic compounds. It's about figuring out at what ratio elements will come together to make the total compound neutral. So there's an example here at the bottom of your screen, right? If calcium tends to make a charge of +2 and the chlorine ion tends to make a charge of -1, they can't come together at a ratio of 1 calcium to 1 chlorine because calcium is +2 and chlorine is -1, right? They're going to have a net overall +1 charge that hasn't been taken into consideration. So the ratio they come together at is 1 calcium to 2 chlorines, making the final formula CaCl2. So what you got to know to be able to do this are the charges of the elements on the table. Okay, remember our main group charges, the +1, +2, +3, nothing, -3, -2, -1. The transition metals we'll finally deal with in this case. They don't have one charge, as I've told you before. Elements that are in the transition metal region under this, and those ones under the staircase can have multiple. And they could be a +1 or a +2 or a +3 depending on the scenario. So we'll actually identify the charge with their name, and I'll show you that in a second. There are 3 elements on the table that aren't part of our columns and also don't have multiple charges, and those are ones we just have to memorize. So they're the ones at the bottom of the screen here. Aluminum has a +3 charge, zinc has a +2, and silver has a +1. And those are an always thing. So you have to know based on the columns what their charges are, +1, +2, +3, -3, -2, -1. If they're not in one of those columns, then we determine the charge based on the name, unless we're aluminum, zinc, and silver, in which case we just have to have those memorized. So how does the name tell you the charge? Well, when it comes to the name of a metal ion, right, of those transition metal ions, the way we write down the cation portion of an ionic name is we name the atom, like for example Cu would be the name copper, so that's part of the name, just copper. And then whatever the charge is on the ion, we include that charge within parentheses as a Roman numeral. So if you have the charge of +1, you include in parentheses the Roman numeral 1. Charge of +2, in parentheses Roman numeral 2. The highest charge we usually go up to is 4, so you will see commonly Roman numerals 1, 2, 3, or 4. Biggest mistake people make is they think the Roman numeral means how many atoms I have, and that's not the case. The Roman numeral simply tells us what the charge is on the cation portion of our compound. Without that Roman numeral, we can't figure out the name. So take a look at the bottom of the screen where we have FeO and Fe2O3. The reason we're getting two different compounds is because the iron cation here is two different charges. Okay, depending on the scenario, iron can have a +2 or a +3. If we name that compound simply iron oxide, we don't know if it's FeO at a 1:1 proportion or Fe2O3 at a 2:3. By saying it's iron 2 or by saying it's iron 3, now there's one specific formula we can generate. So then when you're naming something, you're trying to name it so there's only one possibility. If there's more than one formula that can be generated, it's not a good enough name. Now don't forget the exceptions, aluminum, zinc, and silver. They don't include a Roman numeral, and it's because aluminum's always 3, zinc is always 2, silver's always 1. So essentially when it comes to naming ionic compounds, the cation portion, if you know the charge, you don't include a Roman numeral. Okay, so like for column 1, all the alkali metals, you don't need a Roman numeral because they're always the same charge. Aluminum, zinc, and silver, always the same charge. Every other metal, so the ones in the transition metals and under the staircase, they use a Roman numeral because they can have multiple potential ions. So how do we make the name? First thing we do is we name the cation. Okay, so anytime you have an ionic compound, you'll have a cation followed by an anion. Number 1, name the cation. The way you name it is you name the atom that's presented and you include a Roman numeral if needed. So taking a look at this screen, we have the sodium, iron, aluminum, and another iron. Though we would name sodium simply sodium because it doesn't need a Roman numeral. We know its charge. That iron +2 we would name as iron 2. Aluminum would simply be aluminum, and then iron would be iron 3. Next part of the name, we name the anion, the nonmetal portion. And the anion is similar to with the molecular naming. We name it whatever the nonmetal is, but the ending is IDE. So that's chlorine, you would name it chloride. Oxygen, you would name it oxide. And then you just put them together. So here's some examples. I'm going to run through on the board for you. So first one up here, NaCl, you name the cation first, which is simply sodium, no Roman numeral needed. And then you name the second part, which is the Cl part, which is chlorine, has to end in IDE, so it's chloride. Next one, we have iron and chlorine. Iron is a transition metal, so I'm going to need a number in the parenthesis. To figure out the number in the parenthesis, come back to your compound. However many negatives I have here, I need positives. So chlorine is always -1. I have 2 -1s for a total of -2, which means iron has to be +2 to balance it out. So this name is iron 2 chloride. FeO, though, on the other hand, we can look at 2, right? Oxygen is -2. Iron is still +2 then. So this would be iron 2 oxide. Aluminum down here, aluminum doesn't need a Roman numeral because it's one of our 3 memorized, aluminum, zinc, and silver. So this is just aluminum chloride. A couple more examples. We've got sodium with oxygen. Again, sodium doesn't need a Roman numeral, so that's just sodium oxide, straight up. Down here, iron chloride. Iron's going to need a Roman numeral. It's a transition metal, right? Chlorine, again, is -1. I have 3 of them for a total of -3, so this iron has to be +3. So that's going to be iron 3 chloride. Down here, all oxygens are -2 for a total of -6, which means this has to be, to get to a +6, this has to be +3, right? Because 3 times 2 is where I can get a 6. Aluminum, we don't need a Roman numeral for, so this is just aluminum oxide. So you can see it's awesome to name ones that don't have a Roman numeral because you just name them. Metal anion, or metal cation, and then the anion, and that's it. If you need a Roman numeral, you need to determine it based on the charges presented. Writing the formulas I think, is where the trick is. The name, it's just a question of remembering Roman numeral or not, but generating a formula is where you have to use some math. The big thing to remember about making a formula for ionic compounds is that in the end, when the cation and the anion come together, they have to make a neutral bond, right? We can't have an overall charge left over. Life is neutral. You don't get shocked every time you interact with salt. In order to make a neutral compound, you can use more than one of any given ion. For example, if we were given the name magnesium nitride, they don't come together with one magnesium and one nitrogen because magnesium is a +2 charge and nitrogen is a -3 charge. So the question becomes, at what ratio can I bring these two together so that when I add up how many positives are present, how many negatives are present, I end up with a 0 charge. It's what's called the least common multiple, if you know anything about math. The least common multiple between 2 and 3 would be 6. So you'd need 3 2s and 2 3s to get to 6. And the way we show that then is as subscripts. I needed 3 Mgs and 2 nitrogens to make each one up to a 6. Please notice here when I write the final formula, I don't have the charges written. And that's because even though they're charged particles, we don't present them that way. We present them simply bonded together at their appropriate ratios. There are some tricks to finding the formulas for an ionic compound that I'll show you right now. So if I'm given this name, the first thing I always determine are what are my ions that are present. Okay, copper is Cu, and it has a charge of +2 because of the Roman numeral. Chloride is chlorine, which always has a charge of -1 based on location on the table. So given that information, I have to figure out that least common multiple thing. If that's confusing to you, there's a situation that I usually call a crisscross. And crisscrossing for ionic compounds means whatever the charge is on my first part always becomes the subscript on my second part, and vice versa. So if you crisscross this one, the final formula then would be CuCl2. Again, noting that there's no final charges written, and when I crisscross, that charge becomes a subscript. You don't ever write a 1, right, so that's not present, and this is correct. This is the lowest common ratio of these two things as they come together. For aluminum iodide, I write down my ions again. Aluminum's always a +3 because that's what it is. I memorized it. Iodine's -1. So the lowest common multiple between them is 3, or I can crisscross them, which means this will be the final formula. I need 3 iodines and 1 aluminum. I write down my 2 ions first. Calcium's +2, selenium's -2. And this is the one time crisscross can lead you to difficulty. Okay, if I bring these down, I would write a final formula of Ca2SE2, which is not correct. It needs to be the lowest common multiple between the two atoms, their lowest common ratio they come together at. 2 to 2 can be reduced to 1 to 1, and that's the final answer. And this is the one time you can get tripped up if you're not careful. Silver oxide. Silver I have memorized the charge of +1. Oxygen is -2. If I crisscross that or know the lowest common multiple is 2, that's my final formula, Ag2O. Chromium 2 fluoride then. Chromium, I'm being told, has a charge of +2 because of the Roman numeral. Fluorine's always -1, so if you crisscross that or figure out the lowest common multiple, that's your final answer. So one thing to notice, I'm always writing the formula in the order of the name, metal, then non-metal. Always, 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 always. There's no exception to that. And then the biggest thing to keep an eye on is that your Roman numeral here is becoming your charge, never how many. That's all the content for naming ionic compounds. Biggest thing is practice. So watch this twice if you need to make sure you're actually kind of understanding what the rules are. Go ahead and do the form and have a nice night.